Okay, we're going to continue our investigation of magnetic fields and magnetic forces. So I want to review first what we did in the last installment, and that was to consider forces on wires carrying currents when they're in a magnetic field. So the situation I've drawn here is a magnetic field going across a table and a current in a wire, the orange one, going across the table also. And the two are perpendicular to each other. Okay, in that case, with this orientation, we found that the force was upward on the wire. We had another way of drawing that over here, the same situation, just simplified to remind ourselves of the orientations. So we had a right arm rule where you put either your arm in the direction of the current and you rotated your hand until the magnetic field came out of your palm, and then your thumb pointed in the direction of the force. Okay, and we used this symbol, a circle with a dot in the middle to indicate an arrow coming towards you. So that's a vector coming out of the screen, whereas a circle with an X on it was a vector going into the screen. So this allows us to get 3 dimensions in a flat plane, or a diagram with 3 dimensions in a flat diagram without having to try to draw 3-dimensional drawings. Okay. The other thing we talked about was the magnitude of the force. Now this gives us the direction. The right-hand rule gives you the direction. But the magnitude is a little more complicated. We need to be careful in cases where the field isn't perpendicular to the current. Okay? So down here, I've drawn another situation, a little more general, where the field and the current aren't exactly perpendicular. They're not parallel, but they're not perpendicular either. And the rule is that what you need to do is find the perpendicular component of the field, this guy over here, the length of that side. So you know the strength of the magnetic field is this length, but the strength of the perpendicular component is that part. Okay, so the point is that that component is perpendicular to the current. That's the wire carrying the current. Okay, so if you find that length, then you can use this equation down here to calculate the strength of the magnetic force. So if we take, up here on the table again, we take a length of wire, we just chop it off, length L. Of course, we need the rest of the wire in order to carry the current to it, but we're just going to calculate the force on that piece of wire. Okay, so it's proportional to the length and the current and the magnetic field perpendicular to the current. All right, so that works great on any section of wire in a uniform magnetic field. Now, of course, as we noticed here, this wire isn't just a straight section of wire. It's made up of a bunch of straight sections of wires, with bends in them. So we could take each of these sections of wire and calculate the force on them, but we might be interested in what's the net force on the whole thing. Okay, so and it ends up that currents are always in loops, so we have to deal with current loops in their entirety. So let's do that example. Okay, so let's imagine a loop of wire. And we're going to do this flattening out. We'll draw the vectors that are going perpendicular to it as dots. So let's start with a current going this way, clockwise or counterclockwise around the loop. And we'll assume that the magnetic field is going down into the screen. I don't know why I said down, because for me it's down. I'm looking at a tablet sitting on my desk. For you, it's probably on your laptop, away from you. Your screen is probably vertical and mine's horizontal. So I say down, but I should really say into the paper. And so this is one of the places that gets really complicated. You have to be careful about your orientation and what you mean by it. It's sort of like we look at a map. Say we do the U.S. So you might, this is, the map is hanging up on the wall, yeah? And so you say, okay, well, north is up. But that doesn't really make any sense, right? Because north isn't up. North is a horizontal direction. But because the map is on the wall, the north in that diagram is up. So don't let yourself be confused by this. Just make sure you know what you mean by directions. Okay. So here we go. So now we want to find the forces on the four sides of this loop. So go ahead and do this before I do. Calculate the direction of the force using the right-hand rule. Calculate the direction of the force on this section of wire here. Just the top. Okay. So you arm is aligned with the currents, sort of like across you, yeah? So you get the arm out in front of you going across your body. So use your whole arm until your forearm is easily going in the direction of the current. Now you rotate your hand until the field is coming out of your palm. Okay, so if you're on your laptop here and this is vertical, that means your palm is facing away from you. Then your thumb, sticking out of your hand, is in the direction of the force. So in that case, it's this way. Okay, now let's do the same thing on this wire here. Now, again with this up vertically on the vertical surface, your arm will be going down towards the ground in the current, yeah? So then you rotate your hand again until your palm is facing away from you. This is kind of an uncomfortable one to do. So then your thumb is pointing to the left. Okay, I'll leave you to practice on the other two sides. Make sure that you get these right. Okay, so they all end up pointing inward. Now, we could just as easily have imagined that same loop, but with the current going the other way. Okay, so let's put the current going clockwise instead. The direction of your arm has to flip. And I'll leave this also as an exercise to show that the forces all flip also. Now, interesting thing here is that one of these is unstable and the other one is stable. I want you to just think about if you, suppose you had a hula hoop and you had, if you're pressing on the two sides or pulling on the two sides. So you can either push in on the sides or you could pull out on the sides. One of them is more stable than the other. if you think about it, this one, those two forces are balanced. That's true. But if that loop shifts a little bit, so let's draw it like this. There's our loop from the side. So we flipped this thing up this way. So we're just seeing this lower edge. Okay, so then we're pushing on it like this. These are these two forces. Now, if this lifts a little bit somehow, then those two forces are going to want to rotate this. The net force is 0, but this is going to cause this end to go that way and that end to go that way, so the thing will rotate. In this case, if I'm pulling on those and it's at an angle, the rotation will be back this direction, which will lead it naturally to go back to here. So this one is stable, and this is unstable. So they both have 0 net force, but one of them is unstable in that it would like to rotate. Okay, so it's not stable under rotations, whereas this one is stable. So what that means is if this loop is in this orientation and we give it a little bit of a lift in one direction, it will by itself flip over and go to this one. Okay, so what we have here is a motor. If we install an axis on this thing, so let's put an axle through this thing so that it can rotate around this axis and not the other one, then this will naturally, if we start in this in orientation of the current, it will naturally go to this one, if that makes sense. Now, by putting this axis through here, it prevents this force and that force from becoming unaligned. Okay? They're not going to be, they can't possibly get unaligned because they're held so that they stay always like this. But these two forces can become unaligned and cause a torque. All right, so we're going to redraw this whole thing from the point of view over here. So that's your eye. And you're looking at this thing from here. So what would it look like? Well, we would see the loop. And we'd see the currents now, but what does this current, get rid of this extra stuff here. What does this current look like from this point of view? It looks like an arrow coming at you. And what does this current over here look like? It looks like an arrow going away from you. Now, because this force and that force are balanced, we're not going to bother calculating them. So we don't need to draw the currents going here. If we did, you'd have one current going this way in the one closer to you, and another current going like that in the other way farther from you. You can see why they would cancel. But we're not going to bother with those because we know they cancel. Okay, so we'll also draw the axis of rotation here. All right, and we could add the forces in. You could use the right-hand rule if you want, but we know what they look like from this point of view. They're just going up and down just like they did before. Okay, this shifting, from, this is like one view to another view. So here we're above the loop. In this picture, we're above the loop looking down on it. Here you're at the side of the loop looking at it. Ends up being indispensable when you're dealing with magnetic fields because of the fact that the three vectors aren't all in the same plane. The current, the field, and the force are not in the same plane. So in this view here, what direction is the field? This is a good practice. What would the field look like from this guy's point of view? So you have to imagine over here, what we're seeing is just the tails of the arrow. That's what the little X is. So we see the tails of the arrow, so the head must be down below it someplace. So the left, this guy's left, should be the tail, and that guy's right should be the head. So the magnetic field here is going like this. All right. So now the reason we wanted to draw it from here is that now we can look at what would happen as this loop rotated. So we start up here and we rotate down to this position. Okay. So what we've drawn is this final position, but it started like this. And in between, we had all the other angles. Yeah, so it could have been, it could rotate either way because it's an unstable equilibrium. It depends on which way it starts. So let's suppose it's going to go clockwise. So in between, we would have something like this. So it starts like this, a little bit later, be like that. Sometimes later, like that. Okay, so that would be the transition. Okay, so to measure the angle, we're going to use the area vector. Now, if you remember, we said that if you had any area, you define the vector to be normal to that surface. Okay, so we do this with current loops also. They contain some area. Yeah. So if you lay it so that the current is going counterclockwise, the vector points out that way. If it is clockwise, then the area vector points down into the paper, or down in through the air the other direction. Okay, so here we have the area vectors going like this. Okay, so we start off in this diagram with the magnetic field is this way. Yeah. So we start out anti-parallel, so the angle between them is 180 degrees, and then it decreases like that. So this is, oops, we're talking about this angle between the two. The angle between the direction of the area and the magnetic field. All right, so we're almost there. So what do we want to do now? Let's look at a general configuration. So we'll start off something like this where the angle is less than 90. So we'll draw the normal. Draw the magnetic field also. Call that angle theta. All right, the nice thing here is that as this rotates, the direction of the current hasn't changed. You see? The position has changed, but the direction is always just, this one is always out of the paper. This one's always into the paper. The direction of the magnetic field hasn't changed either. So the direction of the force is always the same. Okay? Okay, so these are each going to cause a torque to rotate it that way, to try to get to 0 degrees. So what is the torque? Probably didn't write it this way last time. You need to take the perpendicular component to one of those vectors. What is R? R is pointing from the axis of rotation to the place where the force is applied. Okay? So if we draw this more carefully, we need to get a little bit bigger so we can see our perpendicular. Well, maybe it's clear enough. We'll just make it bigger. And make the pen smaller. So we need to break this R into components. This is going to be the angle theta. Now ask yourself, our vector is this side, the hypotenuse. And now you have to find which is our parallel and which is our perpendicular. We've got these two sides. Which is parallel to the force and which is perpendicular. Okay, so this is the one we need, and that's r sine theta. Okay. So that allows us to calculate the force. R F sine theta. Now the force, since the field and the current are perpendicular, is just the length of that wire times the current times the field. Now that's this torque. This one also causes a torque, so the net torque is twice that. I'm going to do it like this. Because this is the area of the loop. If we draw the loop this way where we can see it again, L was that length there. This is that side, right, with the current on the end. Here's the axis of rotation. Those are each R. So this length is 2R. So the area is the length, the product of the length of the sides. So that's this. So The odd thing is that we derived this for a square, but it actually doesn't depend on the shape. You can take any shape you want, put an axis through it, and you get the same result, oddly. So, I mean, that'd be kind of a weird shape to take, but maybe a circle wouldn't be so odd. Okay, so it just depends on the amount of current going through there, the area, and the magnetic field strength going through it. And the angle between the normal to this area. If I got backward, yeah, that's right, it should be. The area is going that way. And this magnetic field. All right, so this is a motor. In a sense, it's causing a rotation. If you think about most motors, what are they? They're rotational motors that cause things to spin. But you might be wondering, well, this isn't spinning, this is just turning halfway. Once it's gone from here to there, it's turned 180 degrees. But once it gets to here, it's not going to keep rotating. It's happy to be there. Okay? Now, the thing to notice is the only difference between these two. I'm going to redraw this a little bit because it's kind of a mess. The loop is just a loop. What's different here is the direction of the current. You can see the current has reverse directions. If we look at it up here, you see that also. Here are the currents. On this top one, current's going counterclockwise. Here it's going clockwise. So in any motor, what you have to do is essentially once it's reached this position where it's happy, you have to flip the direction of the current. And they all do it by different means. It used to be mechanical. There's like fancy ways of hooking the wires up from the loop to connectors. It was all very natural because as it rotates, you connect the other way. That method is essentially like this. You have your loop with the two leads of the wires coming out. You connect that to essentially a pipe. Okay, so you weld this into both of them, and then you cut the pipe in the middle. Okay, so that they're not electrically connected anymore. So now looking at it from the end, we've got this pipe which comes around like this, another one like that. And one of these is connected to this side of the loop, and the other one's connected to the other side of the loop. And now you put some brushes. They're literally brushes with metal hairs that connect up to the battery. Okay, so when this completes the circuit through the little metal wires, gets the current through there. But the point is that this guy rotates. So as it rotates, I suppose this is the unstable one. It's going to rotate 180 degrees. The coil will rotate, and it carries, this is on the axle, right? The axle is mounted on this thing. So as it rotates, these guys rotate too. And if you see what happens is it gets to some point where these brushes are connecting to this, connecting to that, but as it rotates enough, it no longer connects there, it connects to the other one. And so then the other is essentially like running the current in the opposite direction, which is exactly what you wanted. That's not so much how you've probably heard of, maybe you've heard of brushless motors. They don't do it this way anymore. You use electronics to switch the direction. So there's transistors and they're sensing the orientation of the axle, and when it gets to the right place, they change the direction of the current. It's more efficient and longer lasting. These are the things that would wear out. The brushes always need to be replaced. It's also mechanically they're rubbing on here, so it wears out this pipe also. So we mostly moved beyond that in modern motors. They still exist in cheap ones. It's still an easier way to make it. It doesn't take, it's all mechanical. It doesn't take anything. I mean, you could make one actually. If you look on YouTube, there's a lot of people making simple motors with just a battery and a coil of wire. There's simple ways to do this system here. Okay, there's one other thing that is similar to this, but it's a linear motor. And you're actually using it right now to listen to me. So I've recorded this. It turns it into a digital signal. The digital signal gets sent along with this video. Someplace in your computer, it unwraps that digital signal. And what that digital signal is the motion of the pressure waves. So sometimes the pressure is high, sometimes the pressure is low, and it has that signal. So you have some signal that's oscillating that represents the sound of my voice, or that is the sound of my voice. So the same thing that the air would be doing to your eardrum. Of course, this is a voltage now. It's been encoded in the computer as a voltage. So what you do is you take that and you send that voltage through a loop. Okay? So now we have a current. That varies with the voltage. I guess I should stick to my color scheme here. Of course, the direction, since this voltage is sometimes negative, sometimes the current will go the other way. Sometimes it'll be strong, sometimes it'll be weak. All right, so now that's not enough. What you do is you surround this with a magnet, permanent magnet, with the electric field going in radially towards this. Okay, so this is all in a plane. It's a little hard. I didn't draw it very well, but you have to imagine it's laying flat on a table. Those magnetic fields are all coming towards it in the plane of the table, and the loop is in that table too. So then, at this moment, with the current going counterclockwise like that, if you look at the force on all of those currents, we have to divide it up into little current segments. There's one here, there's one there, there's one there, there's one there, all the way around. And we calculate the force on each of these. They're not in the same direction, so you have to do them individually. But oddly, since we've engineered the magnetic field, it's actually rotating at the same rate. You see? They're always at the same angle. They're always perpendicular to each other. And if we use the right-hand rule, you'll find that the force on all of them is just straight up out of the table. So that means that this loop of wire is going to be forced up. If the current was negative, it'd be forced down. So now we have this loop of wire jiggling around, just like my vocal cords did. So to make it so that you can hear it, you take that loop. It's actually not a single loop, but a bunch of loops. They actually go around many times to get more force. So it's like a little tube. And then you connect a cone of paper to it. Hopefully you can see that. So now if this cone is connected securely to this wire loop, when the wire loop moves, the cone moves too and pushes air, and you can hear it. So that's a speaker. This is one of the last pieces that you have to mount it. So there's usually a flexible membrane going around the edge that keeps it stable but allows it to move. Okay, so all speakers are pretty much based on this. There are some exotic ones that are different, but this is the majority of them. So right now your computer for sure has one of those in there. If you're listening with headphones, it also does. They have tiny, tiny little ones in those earbud things. Okay, so that's 2 applications, motors, speakers, that use magnetic field to cause motion. Okay, so currents in magnetic fields create forces. You can use those forces to move things. All right.